You are born with 16 types of color receptors in your eyes. Humans have 3. You can see wavelengths of light that no other creature on Earth perceives. Ultraviolet, infrared, polarized light bending in directions that do not exist in any human visual framework. You are the most visually advanced animal that has ever lived. You use this extraordinary gift to find things to destroy. This is the mantis shrimp, and almost nothing about its existence is what you would expect. Bright orange, electric blue, deep violet at the edges shifting into something with no name in any human language. It is approximately the length of your hand. It has just spotted something moving at the edge of its territory. The something is a crab. The crab is twice its size. The mantis shrimp does not reconsider. The strike happens in 5 milliseconds. To give that number context, the fastest human eye movement, a blink, takes 150 milliseconds. The mantis shrimp's strike is over 30 times faster than the fastest thing your face can do. The mechanics of how this is possible took researchers decades to understand because the strike happens too fast to observe with conventional camera equipment. High-speed cameras operating at thousands of frames per second finally captured it, and what they found redesigned how biologists think about biological force generation. The mantis shrimp does not generate its strike through muscle power alone. It uses a saddle-shaped spring mechanism built into its arm, a biological energy storage system that compresses like a loaded crossbow and releases all stored energy simultaneously in a single catastrophic discharge. The result is a strike that reaches the speed of a bullet leaving a gun. The scene shows the crab shape moving across the frame. The mantis shrimp shape shifts position, then the strike. A single frame. The crab shape reacts, shell fracturing, body tumbling backward across the white background. The mantis shrimp stands exactly where it was. It did not move. Only its arm moved. The force of the strike creates something called cavitation. When an object moves through water fast enough, it creates a pressure differential so extreme that the water itself tears apart, forming bubbles of near vacuum at the point of impact. These bubbles collapse almost instantly, and the collapse releases a second shockwave following the first. The crab gets hit twice, once by the physical strike, once by the cavitation collapse less than a millisecond later. Aquarium glass cannot withstand repeated mantis shrimp strikes. Aquariums that house mantis shrimp must use specialized thick acrylic enclosures. Conventional glass tanks fail. The mantis shrimp strikes it once. A crack line appears. Strikes twice. The crack expands. The third strike and the glass shape shatters outward, pieces scattering across the white background in a slow explosion of fragments. The mantis shrimp moves through the gap. It does not look back. There are 2 types of mantis shrimp, spearers and smashers. The spearer hunts soft-bodied prey, fish, worms, anything with yielding flesh that a barbed spear can penetrate and hook. Its weapon is a pointed impaling structure that fires with the same cavitation-generating speed but delivers a different mechanical outcome, penetration rather than shattering. The smasher hunts hard-shelled prey, crabs, snails, clams, things protected by calcium carbonate armor that took millions of years of evolution to develop as a defense against predators. The smasher treats this armor as a temporary inconvenience. The scene shows a snail shape moving across the frame, shell thick and rounded, the kind of shell that deflects attacks from most predators. The smasher mantis shrimp moves alongside it, matching its pace for a moment, then the strike. The shell does not crack. It shatters. The pieces scatter across the white background in a spray of fragments that settle slowly in all directions. The mantis shrimp moves to the exposed prey. The shell, the product of millions of years of evolutionary defensive engineering, lasted approximately 5 milliseconds. Now come the eyes. The mantis shrimp has 16 types of photoreceptor cells in each eye. Humans have 3: red, green, blue. And from those 3, we construct the entire visual world we experience. For years, researchers assumed 16 receptor types meant the mantis shrimp experienced a visual world of incomprehensible richness. If 3 gives us what we have, 16 must give something exponentially more complex. They ran the color discrimination tests. The results were completely unexpected. The mantis shrimp is actually worse at discriminating between similar colors than humans are. The 16 receptor types are not for creating richer color experience. They are for something faster, a parallel processing system that identifies specific wavelengths instantly without the comparative analysis that human color perception requires. Human color vision works by comparing inputs across 3 receptor types. The brain calculates the relationship between signals and constructs color from the comparison. The mantis shrimp does not compare, it identifies. Each wavelength hits a specific receptor and the answer comes back immediately. This color, this polarization, this UV signature, yes or no, detected or not detected. It is less like having better vision and more like having a faster computer running simpler but more numerous programs simultaneously. A human eye icon struggles to distinguish them, the shapes blurring at the edges, overlapping, the icon indicating uncertainty. The mantis shrimp eye processes both instantly. 2 clean, separate signals, no comparison required, identification immediate. Speed over depth. Identification over interpretation. A system built not for appreciating the world, but for responding to it without delay. The mantis shrimp lives alone. This is not a preference, it is a biological necessity that emerges from the combination of its weapons and its temperament. The mantis shrimp is territorial with a consistency that makes every other territorial animal look casual about it. Its burrow, a tunnel it excavates in soft sediment or finds in rock, is the center of its entire existence. Everything within a certain radius of that burrow entrance belongs to the mantis shrimp. Anything that enters that radius, regardless of species, regardless of size, regardless of whether it poses any realistic threat to the mantis shrimp, gets the same response. The scene builds. The mantis shrimp at the center of its territory, indicated by a circle drawn around the burrow entrance. A fish shape drifts too close. Strike. The fish shape tumbles away. A crab enters the circle from the other side. Strike. The crab retreats. Another mantis shrimp approaches. A different colored shape, same body structure. The territory owner moves towards it immediately. The approaching mantis shrimp retreats. The territory owner returns to the burrow entrance. The circle is maintained. Nothing has successfully entered it. The only exception to the solitary existence is breeding, and even this is unusual. Mantis shrimp form pair bonds. In a species defined by aggression towards every living thing that approaches, the formation of a stable pair bond between 2 animals, each capable of striking with bullet speed, requires something more than simple tolerance. Researchers observing mantis shrimp pair behavior found something they did not expect: mutual grooming, shared burrow maintenance, extended periods of proximity without conflict. 2 mantis shrimp shapes in the scene, one slightly larger, one slightly smaller. They move alongside each other near the burrow entrance. The aggressive response that fires towards every other living thing is absent. They occupy the same space. Neither strikes. The pair shares the burrow and defends the territory together, doubling the strike capacity available at the entrance of a tunnel that was already defended by one of the most powerful weapons in the ocean. The scene shows an octopus shape approaching the defended burrow. Octopuses prey on mantis shrimp when they can catch them undefended. The pair responds simultaneously, 2 strikes from 2 directions.
The octopus shape retreats with speed. The pair returns to the burrow entrance. Together, they are something genuinely difficult for even an octopus to approach successfully. But the pair bond exists in a context of almost complete social isolation from every living thing the mantis shrimp encounters. The world of the mantis shrimp is two circles: the territory circle, which is defended with absolute violence, and inside it the pair, which is protected with the same intensity directed outward. Everything beyond the territory circle is a potential threat. Nothing within it is safe except the pair itself. The mantis shrimp strikes its prey so hard that the impact generates light. This is called sonoluminescence.
The conversion of sound energy into light energy during cavitation collapse. When the pressure bubble created by the strike collapses, the implosion is violent enough to produce a flash of light at the point of collapse. It is brief, visible only with high-speed cameras, not visible to the naked eye in the dim light of the ocean floor. But it happens. The scene shows the strike in slow motion, the arm extending, the impact point, the cavitation bubble forming as a near-perfect sphere at the point of contact, and then the collapse. And at the moment of collapse, a brief flash, a single frame of light in the white background brightening and then immediately returning to normal. Light from violence. Energy so concentrated that matter itself responds with luminescence. The mantis shrimp does not know this happens. It is not trying to produce light. It is simply striking with everything its biology contains. The light is a consequence of the excess. Now the prey. A clam shape sits on the sea floor, shell closed. Internally, the clam is doing nothing except filtering water, one of the most passive existences in the ocean. Its shell has been effective against most predators for its entire life. Starfish move too slowly. Most fish cannot generate enough force. The clam's strategy is simple and has worked across hundreds of millions of years of predation pressure. The mantis shrimp arrives. It examines the clam, moving around it, the 16 receptor eye processing the shell's surface, identifying the stress points, the thinnest areas of calcium carbonate where a strike will be most effective. Then the positioning, precise, deliberate. The mantis shrimp places itself at an exact angle. Then the first strike. The shell shape cracks. The clam's strategy, refined across geological time, has met its mechanical limit. The second strike. The shell opens. Total elapsed time from arrival to access under 3 seconds. The clam had no behavioral response available. Nothing in its evolutionary history prepared it for an organism generating strike forces in thousands of newtons at bullet speed. The clam's defenses were calibrated against a different world, a world that did not contain the mantis shrimp's specific combination of speed and impact energy. The mantis shrimp feeds. At night, the mantis shrimp retreats into the burrow. The burrow entrance is sealed from inside. The mantis shrimp rocks it with its body, facing outward, weapons positioned at the opening. Anything attempting entry at night meets the same response as anything attempting entry during the day. There is no off switch. The scene shows the burrow in cross-section, the tunnel dropping down through the sediment, the mantis shrimp positioned at the entrance facing outward. Around the burrow on the white background, the ocean floor extends in every direction, empty, other shapes moving past at a safe distance. The mantis shrimp watches all of them. Hours pass, nothing enters the territory. Dawn arrives and the mantis shrimp moves back out. This is the rhythm. Emerge, defend, hunt, return, block, wait. Repeat for 20 years, the lifespan of a mantis shrimp, extraordinarily long for a crustacean of its size. 20 years of strikes, 20 years of defended territory, 20 years of eyes processing the world in 16 dimensions, while everything nearby keeps its distance. The mantis shrimp's dactyl club, the striking arm structure in smashers, should theoretically fail. The forces it generates on its own surface during a strike exceed what should be mechanically possible for a biological material. Every time it strikes, it is essentially hitting itself with forces that should fracture the club. It does not fracture. Researchers analyzing the structure of the dactyl club found a helicoidal arrangement of fiber layers rotating around the central impact surface, a biological design so effective at distributing and absorbing impact energy that materials engineers have spent years attempting to replicate it in synthetic materials for use in aircraft panels, body armor, and helmet construction. The mantis shrimp solved the problem of repeatedly generating extreme impact force without self-destruction millions of years before humans started designing materials. The solution was already here, moving through the deep water, defending a burrow, striking at everything that came close. The scene pulls back. The white background expands. The mantis shrimp is small now in the center of the frame, vivid against the white, surrounded by empty space. Other animal shapes drift at the edge of the frame, keeping their distance. A fish shape, a crab shape, a small octopus, all of them maintaining the margin that experience has taught them to maintain. The mantis shrimp does not move towards them. It does not need to. Its territory is intact, its burrow is secure, its weapons are functional. It turns and descends back towards the burrow entrance and disappears inside. The white background holds for a moment, empty, the other shapes drifting at a distance, the territory circle implied around the burrow entrance, even though nothing marks it visibly. Then another mantis shrimp shape appears at the edge of the frame, smaller, younger, moving in the direction of the burrow. It crosses the invisible boundary. From inside the burrow, a single arm extends into view. The younger shape retreats immediately. The arm withdraws. The burrow entrance is empty again. The territory remains exactly what it was before, defended without discussion, maintained without negotiation, absolute in the way that only biology operating at the edge of its own mechanical limits can be absolute. The mantis shrimp sees colors you cannot name, moves faster than you can blink, hits harder than physics seems to permit, lives alone for 20 years in a burrow it treats as the only thing worth protecting. It is not the largest predator in the ocean. It is not the apex of any food web. Octopuses hunt it, fish eat it when they can. But in the space it occupies, in the radius around the burrow entrance that it has claimed as its own, it is completely, mechanically, biologically unmatched. The world around it evolved to keep its distance. That is the mantis shrimp's only real legacy. Not the prey it consumes or the burrow it excavates, but the empty space around it, maintained by force, 20 years at a time. The most violent animal that has ever lived is also, in the end, the most alone. Drop in the comments which part changed how you see it. Most people say the club, the moment they learn that aerospace engineers are studying a crustacean's arm because they cannot replicate what evolution built there. Because that detail reframes everything. It means the mantis shrimp is not just a violent animal. It is a violent animal that solved an engineering problem humans are still working on, and it solved it without a laboratory, without any of the tools we consider necessary for solving hard problems. It just kept striking for millions of years, and the arm got better.